Hello everyone, and welcome to my unfinished basement where we will be having class from for for the foreseeable future, hopefully just the next 4 weeks. So I'm going to pick up right where we left off when we were talking about the Coulomb force before coronavirus hit and turned our whole world upside down. So let's get to it. All right, so the Coulomb force describes the force between two charged bodies. So if you have a charge q1 and a charge q2, then the vector form of Coulomb's law tells you that the force between them, that the force that is exerted on q1 by q2 will be equal to k, the Coulomb constant, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared, times the product of the two charges, q1 and q2, divided by the distance between them squared. So that's the magnitude of the force. And the direction will be along that unit vector pointing from q2 to q1. Okay, so note here, this is these indices here tell you that this is the force on q1 by q2, and this tells you that the force has as its direction in the direction of this unit vector pointing from q2 to q1. So you can take this little this unit vector here, right, and just kind of pick it up and move it over here, right, and that tells you the direction that the force exerted by q2, the direction of the force exerted by q2 on q1. So the force on q1 by q2 points off in this direction here. So there's another way that you can write this law. It can also be written like this. This is sometimes an easier computational way to write things. If you don't want to have to bother to get the unit vector from the displacement vector here, then what you could do is write it in terms of the displacement vector itself. So the displacement vector is this vector here that points from q2 to q1, and its magnitude of this displacement vector is just the distance between the two objects. So this is this is just less of an equation and more of just telling you the notation. And so if you take this displacement vector and divide it by the length of the displacement vector, you'll get a unit vector that points along that direction from q2 to q1, and that will have no units, and its length will be 1. So if you take the length of the unit vector, r21 hat, that will be equal to 1. By the way, I always refer to this as r21 hat. If you're watching, say, Walter Lewin lectures, he refers to it as r21 roof. Okay, so it kind of looks like a hat. It kind of looks like a little roof over the top of the vector. Either one is, you can use whatever words you would like. They all mean the same thing. So what you could do then is write, since r21 hat is the displacement vector divided by the magnitude of the separation, you could put that in, right, for r21 hat. And then this equation would look like this, right, where F, the force on body 1 by body 2 is k q1 q2 divided by, now the distance is cubed in the denominator, and that's just because in the numerator we have the displacement vector itself, right? So this doesn't have length 1. It has a length that's equal to the distance that separates, okay, these two here. That's r21. So these are equivalent, right? This is just two different ways of writing it. Sometimes this is the easier way to do the calculation. So I'll do an example of that in just a minute. But for now, let's just go on to doing a 1D example. Okay, so Let's say that we have a system of charges here. There's a negative 2.5 microcoulomb charge here and a 6 microcoulomb charge 1 meter to the right of it. And our example problem states that there's a third charge that is placed in this configuration shown below at the exact point where the net force on the charge is 0. So the charge that gets introduced has a net force of 0 on it because of the location at which it is placed. So the forces due to the two charges at this point are shown to cancel out. And you're asked to determine the location of this point and not the location an infinite distance away. That would also work, right, since the Coulomb force drops off like distance squared. Instead, the non-trivial answer. Okay, so let's think about that. What about, well, could the point where this, say, Q, this charge Q gets introduced be right there? Well, let's just say that you placed a positive charge Q there. Then you would have a force exerted by this 6 microcoulomb charge in this direction, right? It would be repulsive. And you would have, and this object would also exert a force in the same direction, right? Because the the negative charge would then attract this positive charge. So both forces would be in this direction here, off to the left. So that can't be right, right? The force can't be 0 if that's the case, so that can't be right. Let's erase that. What about if the force was over, or what if the charge Q was dropped over here? So let's say it's positive. It wouldn't matter, right? The arrows would just switch around if it was negative. But if it was positive, right, the 6 microcoulomb charge would point that way, and this negative 2.5 microcoulomb charge would point in this direction. So maybe this is a possibility. But further investigation shows that this here is the larger charge. So the force that is exerted by this guy is going to be greater than the one exerted by this guy at the exact same distance, right? Because this one has a larger magnitude of charge. So that means that if we were on this side and we were closer to the larger charge, that would indicate that this force vector here is going to be larger than this force here, no matter what. So that's not going to work, because instead what we need is a point, say, over here, where we can be closer to the smaller charge and closer to the smaller charge, because the closer we get, the larger the force gets, and the smaller the magnitude of the charge, the less the force will get. So we want to be at a point that's close to the lesser magnitude charge and farther from the greater magnitude charge. That's the only way that we can get these things to balance. So let's take a point then over here. This must be where, so let's say if it was a positive charge placed over here, then this is also a positive charge, so this guy would repel. There would be a repulsive force here, and there would be an attractive force here. And it's possible that they could balance at this point. So let's label our charges. Let's call this Q1, Q2, and Q3. And what we need is a coordinate system. So let's set up a coordinate system in blue. Let's say that I'm going to place this, let's make this the plus x-axis. Yeah, let's make this the plus x-axis, right? And we'll make this x equals 0. Okay, and we'll find the point over here where the two things can exactly balance. Okay, so force on the net force on Q1 is going to be equal to the force on Q1 by Q2 plus the force on Q1 by Q3. Q3. So this is a nice one-dimensional problem, right? We know that F12 is going to be in the positive x direction. We know that F13 is going to be in the negative x direction, right? F13 is going off that way, and F12 will go in this direction there. Okay, so if I just look at the magnitude of the forces, I will have, right, just looking at the magnitude of the forces, well, the net force on Q1 has to be 0. We're told that in the statement of the problem. And we're going to have F12 pointing in the positive x direction. So F12 positive direction, and the force F13 is going to go in the negative x direction. So let's go with negative the length of this vector. Okay, so just by way of notation, of course, you can just drop the arrow over the top here, and this means that we're referring to just the length of each one of these vectors. Okay, so now let's put in the values from what we know about the Coulomb force. So we know that the Coulomb force has the Coulomb constant out in front, and then there's this Q1 and Q2 divided by R12 squared. And the direction won't really matter. I've already taken that into account in my setup here. And this will be subtracted from the magnitude of F13, so that'll be Q1, Q3, divided by R13 squared. Okay, and the left-hand side of these is all 0. And you'll note here, right, that there's a Q1 factor, a K factor, and a Q1 factor that's common between both of these. And on the left-hand side, it's 0. So I can divide through by, divide KQ1 on both sides, right? The left-hand side will still be 0. And so what I'll have here is 0 equals Q2 over R12 squared minus Q3 over R13 squared. Or in other words, Q3 over R13 squared must be equal to Q2 over R12 squared in order for the forces to cancel each other out. So R13 is the distance between this guy and x equals 0. R13 is the distance between this guy here and the far charge, right? That's R13. Okay, this distance here is R12 between Q1 and Q2. So you note, right, that R13 is just equal to R12 plus 1 meter. So that's helpful. We can write that in, and we can also write in the values of these different charges. So Q3 is 6.00 microcoulombs, and R13 is R12 plus 1.00 meters squared. And on the right-hand side, I'm going to have 2.5 microcoulombs divided by R12 squared, R12 squared. Now, the reason why I put this in as a positive number is because I know that I'd already taken care of the sign over here. It included the fact that the force will go in the other direction. Our final step then is to just solve for R12, and that'll give us our final answer. So I can cancel out these units here, as I've already done. I can cancel these out, and let's see, I can put 6 over 2.5 on the left-hand side, right, dividing both sides by 2.5, and I can multiply both sides by r12 plus 1 meter squared over here. Okay, note that I'm really not very picky about significant figures, and I don't expect you to be either. So doing this, now 6 divided by 2.5 is about 2.4, and I can take this, I can take the square root of both sides of this to get this quantity, to get rid of the squareds. So I'll have an r12 plus 1 meter over r12 equals the square root of 2.4, and then I can divide the r12 over in those two terms, right? I'll have root 2.4 equals 1 plus 1 meter over r12. So I can subtract that 1 across. It's equal to 1 meter over r12. And then I can flip both sides, and I'll get that r12 equals 1 meter times, so that just gives me the units there, 1 over root 2.4 minus 1. And when I plug this 1 over root 2.4 minus 1 into my calculator, I get that this is about 1.82. So this will be 1.82 meters. So going back to our picture then, where does this actually leave us? So making this to scale, we end up with, well, the meter might be about here, right? So 1.8 meters, we'd probably have this final charge like way over here, and that's where Q1 would end up, where the force, the attractive force between Q1 and Q2 will balance out the repulsive force between Q1 and Q3. So enough of this one-dimensional stuff, let's go to a two-dimensional problem. Okay, so I here have a system of 4 charges that are located in the xy plane, and we're supposed to find the force on Q4. That's this guy here, and we're given the charges as stated here. So let's first just take a look at what the system of forces on this charge is going to be. So opposites attract, and the same sign charges repel one another. So Q3 and Q4 are going to repel one another. So the force on 4 by 3 will be away from Q3. Q1 is positive though, so that will attract Q4. So F41 is going to be in this direction here, and Q2 is of opposite sign, so it will also attract. So F42 is going to be off in this direction. Okay, so the net force on Q4 is going to be the sum of these 3 forces here. So let's find each one of those individually. Now we know Coulomb's law is, right, F4, let's just write it in terms of some arbitrary number I. F4I is K Q4 QI divided by R I4 squared times R I4 hat, or R I4 roof, as Walter Lewin says. So this is a nice way of writing this. This shows that the Coulomb force is a 1 over r squared law. However, if you're like me and you really don't like trigonometry, then you can write this in a different form that'll make your life a little bit easier. Okay? You could write it like this. Okay, Q4 QI over R I4 to the 3rd power R I4 Ri4 now no longer a unit vector, we're talking about the normal displacement vector. So I like it this way. I'm going to solve it this way, and then after that, I will solve it the other way using trigonometry as well. But let's start out with this one. Okay, so let's just make sure that we all know what these displacement vectors are going to look like. So Ri4, right, in the case of, say, if I is 3, this is the displacement vector pointing from Q3 to Q4. R3, 4 is that displacement vector there. R2, 4 is this one here, displacement vector pointing from 2 to 4, and R1, 4 is this displacement vector pointing towards 4 from 1. Okay, so let's write this out then. F for the total net force on 4 is going to be F41 plus F42 plus F43. Okay, so each one of these is going to pick up a factor of KQ4, so I'm just going to pull that right out from the beginning. K times Q4, and we'll have a Q1 over R14 to the third, R14 plus Q2, R24 to the third, R24 vector plus Q3, R34 to the third, R34 vector. All right, so let's just look at the lengths of here. Let's just write down each one of these vectors first. It's a good way to start. Okay, so let's get these each one of these displacement vectors, and since I not only hate trigonometry, I don't really like non-SI units either. I'm going to write them all down in meters rather than centimeters. So R14 is this vector going from 1 to 4 here. It goes down 30 centimeters and to the right 40 centimeters. Another way of saying to the right 40 centimeters is plus 0.4 meters x hat. And it's going to go down 30 centimeters, so that would be minus 0.3 meters in the y hat direction. And what's the length of this guy? The length is just, well, we all know about 3, 4, 5 triangles. This is a 0.3, 0.4, 0.5 triangle. So the length here would be 0.5 meters. Now, what about R24? Well, R24 extends from this guy here, and it goes over to Q4. That's just plus 0.8 meters in the x hat direction, right? 40 centimeters to the origin, and then another 40 centimeters over to Q4. Finally, we have R34. That is this vector here, extending from Q3 to Q4, which goes to the right 40 centimeters and up 30 centimeters, so it goes plus 0.4 meters x hat and plus 0.3 meters in the y hat direction. Okay, and the length of R34 is the same as this length here, right? It's 0.5 meters. And of course, right, the length R24 was just 0.8 meters. That one couldn't possibly be easier because it has one component. All right, so let's go back over here then and put some of these numbers in. So we pulled out a KQ4, and we can put in now, okay, Q1 was 5 microcoulombs, and R14 was 0.5 meters to the third power. R14 was 0.4 meters x hat minus 0.3 meters y hat, plus now Q2 was 5 microcoulombs, and R24 was 0.8 meters. It goes into the third power, and we have an 0.8 meters in the x-hat direction. Right, so that's R24 there. And that last term has a Q3 in it, so that's a minus 5 microcoulombs. And the R34 in the denominator is 0.5 meters to the third power, and our vector then is 0.4 meters in the x-hat direction plus 0.3 meters in the y-hat direction. We're just about done. We just need to go and do some of the math. All right. But some of this stuff is just a matter of plugging in numbers. Minus 2 microcoulombs. It's the charge that goes in for Q4. And for K, well, K is 9 times 10 to the 9th Newton meters squared per coulomb squared, of course, but Q4 is going to be in microcoulombs, and there's this other 5 microcoulomb charge common to all of these terms here. So it would be nice to get this in units of microcoulombs. Of course, there's 10 to the 6 microcoulombs in 1 coulomb, right? So that means this factor is just 1 that I just drew down there. And if I square that, then I can get rid of this coulomb squared in the denominator here. And 9 times 10 to the 9th is going to then be 9 times 10 to the 9th Newton meters squared times 1 over 10 to the 12 microcoulomb squared. Okay, and that will be then, so this exponent is going to go down 12, so times 10 to the minus 3 Newton meters squared per microcoulomb squared. So we can put that in for K. And let's see if there's anything else I can do to simplify before I put things into my calculator. Well, one thing is, so this 5 microcoulomb factor that shows up here and here and here is common to all of these terms, or at least I can distribute this minus through here, and then it's common to all of these terms. So that's helpful, especially when you notice that, okay, this common factor here is the same common factor as the one there, and this term here, this x term here, is totally opposite between these two terms, so that cancels out. Something else that you'll notice is this term here and this term here are exactly the same, so they effectively double up between the two. So I could actually just write that this is 0 and make this into 0.6 meters y-hat, and then I would get rid of this whole ugly last term here. So that's kind of nice. All right, so let's do then some of the math. So remember that when we're adding vectors together, right, you're going to sum together the x components and the y components individually. So all of these x factors here are going to be included together, and I've already underlined in green the y components that you're going to add together. Don't ever add together x components and y components. That's not how it works. So, all right. Well, let's first multiply together our Kq4 and the 5 microcoulombs. So we have a 9 times 10 to the minus 3 Newton meters squared per microcoulomb squared, and we're going to multiply that by minus 2 microcoulombs times, I'm going to pull out this factor of 5 microcoulombs that shows up in each one of these terms here. 2 times 5 is 10, 10 times 9e minus 3 is 9 times 10 to the minus 2. And there was a minus sign as well. And that'll be in units of Newton meters squared, so that's going to be a prefactor for the equal to negative 9 times 10 to the minus 2 Newton meters squared times, and then only the distances remain on the inside of these parentheses here. So there's an minus 0.6 meters y hat divided by 0.5 meters to the third power in that first term there. The second term is just going to have an 0.8 meters x hat divided by 0.8 meters to the third power in the denominator. And that whole third term here, this whole third term has gone away. We canceled that out. So all I have to do is multiply together these last factors, and when I put that into my calculator, I get that the net force on Q4 is negative 0.14 newtons in the x-hat direction, plus 0.43 newtons in the y-hat direction. And I'm going to put a box around this so that whoever grades my work will be able to know exactly what my final answer was. We have an answer, and let's just take a look at what this looks like on the diagram here. So if we go over to the diagram here, so we got something that has a negative x component and a positive y component, right? So it's going to go something like this, which makes sense given the other forces there that made up the resultant force. Okay, great. So this calculation I would call, say, the vector method of coming to the answer. If you like the vector method, that's great. I prefer the vector method as well. If you're looking for another way to solve this same problem, there's also what I'll call the component method. We're going to come to the same answer, but we're just going to use a little bit different way of doing this calculation. And this is important because calculations, this particular calculation and calculations like this are going to be really common. They're going to appear again and again as we're going through this course. You're going to have to get really familiar with vectors and working with vectors in order to get good at electricity and magnetism type of calculations. So there's also the component method. So for the component method, let's just say it's basically a three-step process. Okay, step one would be to get the magnitudes of each force. Magnitude of F. And then step two would be to get components. Then that takes trig, and then you're going to finally include the sign. Include the sign of each individual force that contributes. Okay, so let's do an example, the exact same problem using this component form. Some of you will prefer this. Okay, so first we're just going to get the magnitude of each one of these forces. So each one was going to be, right, we wanted the magnitude F for the force on 4 by I. And we're just going to make this a positive quantity. We don't care what the signs are or what the direction is at all. So this is just magnitude of Q4, right, times magnitude Qi divided by R on 4 squared. Right, there's the factor of the Coulomb, the Coulomb constant there. So let's get that for each individual one. Okay, so F41 then is K Q4 Q1 over R 4 squared. Okay, and so we can plug in numbers. This is 9 times 10 to the minus third Newton meters squared per microcoulomb. squared times Q4 was 2 microcoulombs. I'm not going to care what the sign was, right? And Q1 was 5 microcoulombs divided by the distance between 4 and 1. So if we go back up to our picture here, remember, so for the distance from 4 to 1 here, well, remember that this distance here was 30 centimeters, and this distance here was 40 centimeters. So the hypotenuse here, this is a 0.3, 0.4 meter triangle, so the hypotenuse is 0.5 meters. So there's an 0.5 meters squared here in the denominator. Okay, and F42 then is K Q2 Q4 R 4 squared. That's going to be 9 times 9 minus 3 meters squared per microcoulomb squared times 2 microcoulombs is 5 microcoulombs over, well, now where the distance is 0.8 meters squared. Okay, if I plug these two things into my calculator, I get that this is 0.14 newtons, and I get that this is 0.36 newtons. Okay, and F43, so the magnitude of F43 is exactly the same as the magnitude of F41. So those things are completely equivalent. So this is also just 0.36 newtons. Okay, now I have the magnitudes of each of the forces. What I'm going to do is just take a look at the trig functions now and get their components. And lastly, I'll include the signs. So my resultant force, F4, is going to be, there's going to be some sign, there's going to be some F41. Let's just take first the, let's take F4, the x component first. That's going to be F41x plus some sign times F42x plus some sign times F43x. Okay, so let's take a look at this, at these components then. If I go and back up to my picture here, right, let's just say that I have an angle here that's theta. Okay, so if I want the x component of each of these individual forces, so I can take this angle here, theta, these are exactly the same angles, and this angle here would also be theta, right, because alternate interior angles are congruent, so this theta and that theta are exactly the same. And I just need to take the cosine of theta to get the x component of each one of these forces, right? Of F43 and of F43 and of F41, right? F42 is all in the x direction as it is. So cosine theta is just adjacent over hypotenuse, right? The adjacent side is 40 centimeters long, and the hypotenuse is 50 centimeters long. So this is 4 over 5, or 0.8 is cosine theta. Okay, and that component applies for both F41 and F43. Okay, so I can write that this is F41 times cosine, so this magnitude that I've already gotten is included here, times this cosine theta there, and we've already figured that out, that that is 0.8, so I'll include 0.8 right, plus this times F42 times this. So remember, F42 had only an x component, so F42x is just the same as the magnitude of the vector there, plus some sign times F43 times 0.8, right, times 0.8. Okay, great. So I have the x components for each one. And now I just need to fill in the signs here for each one of these. So going back up to my picture again, right? So the x-axis is pointing along this direction here, right, as indicated. So you can see that F43 has an x component that's in the positive x direction, in this direction here. F41 is pointing in the negative x direction, and F42 is all in the negative x direction. So let's just include those in here. F41 was pointing in the it was pointing in the positive. No, it was point. That was the one. That was the negative x direction. So the negative x direction, and F42 was also in the minus x direction, but F43 was in the positive x direction. Okay, great. Now I just need to plug in the magnitudes for each one of these. So I have a minus, what was F41? F41 was 0.36 newtons, so minus 0.36 newtons times 0.8 plus, I have a negative F42, so 0.14 newtons. And then I have a plus F43 was 0.36 newtons times 0.8. Okay, if I plug all these things into my calculator, what I get is that this is minus 0.14 newtons. Okay, that's the x component. Now let's look at the y component. So F4y would be it's going to have a similar setup. F41y plus F42y plus F43y. And in other words, this is going to be just putting the numbers in there straight away, 0.36 newtons times sine theta this time, rather than cosine theta, plus that same prefactor times F42, which is 0.14 newtons, times, if you remember, right, the y component of F42 is actually 0. So this term is going to end up going away. Plus there's this sine thing. F43 was also 0.36 newtons. And again, there is a sine. There's a sine theta here. So you remember that the triangle had a triangle looked like this, right? And there was a 40, 30, 50 centimeters there, right? And that was theta. So sine theta is then going to be opposite over hypotenuse. So sine theta is going to be 30 over 50, or in other words, 3/5, or 0.6. So that goes in for that sine theta there and there. And we can, so this, we can go back up at the picture now to just get the signs, right, for this step 3. So you can see, right, that F42 has no y component whatsoever. F41 and F43 both have positive y components. So I can fill in both of those as being positive, plus 1, plus 1. That's 0. So this term goes away, and I get, plugging in all of these numbers here, and plugging in 0.64 sine theta, I get that this is 0.432 newtons. So my answer then for F4 is F4 x hat plus F4 y hat, or in other words, minus 0.14 newtons x hat direction plus 0.4. So I will keep up that here in the y direction. So this is exactly the same answer that I got with the other method. Some of you will prefer this method. If you're new to vectors, this one might be easier for you, but you will end up with the same answer.